Hi, welcome to class. My name is Don Lafond, Professor Don, and this week in Cisco 1, we are covering Module 7, Ethernet switching. Now, Ethernet switching is closely related to the data link layer, so you'll see that there's a lot of information that we talk about in this presentation that is connected to the previous module, Module 6. This is not the network layer. We are not talking about IPv4 and IPv6. We are still talking about that physical data link level of our OSI model. If you are here with me live, please hold your questions until the end of the presentation. If you are watching inside of our NetAcad class as a recording, please ask your questions inside of our NetAcad class help forums. And if you're watching this on YouTube, please ask any questions you have down in the comment sections below this video, and I'll try to help, and I encourage you to answer each other's questions. That would be fantastic. I'm going to go ahead and share my screen. Now I have to do a little bit of setup here to get this right. And I'm going to start the presentation. This presentation should be just about half an hour or a little bit less than half an hour. Okay, Ethernet switching. I am going to explain how Ethernet sublayers are related to the frame fields. I'll describe the Ethernet MAC address. I'll explain how a switch builds its MAC address table and forwards a frame. While we talk about that, by the way, I will show you some videos. Those videos are inside of NetAcad. If the quality of my recording is not high enough for you to be able to watch those in the recording, I encourage you to sign into the NetAcad class, or if you are watching this presentation online inside of YouTube, you can get the same videos inside of at the website itexamanswers.net. Again, itexamanswers.net. I am not sponsored by them. I just find lots of good information there. Don't use the multiple choice test questions, answers to the questions in my class, but the videos and the content is the same exact video that's inside of NetAcad. And it'll help you actually do the work. Okay, the Ethernet. Oh, I didn't read the last one. I also described switch forwarding methods and port settings available on a layer 2 switch. Ethernet frames. Now, again, we're talking about the bottom two layers, the data link layer and the physical layer. Ethernet lives at this part, in this part of our OSI model. You can see the breakdown from 802.3 and 802.2, and we'll cover that in just a moment. So Ethernet operates in the data link layer, the physical layer. I just said that. It is a family of network topologies defined in the IEEE 802.2 and 802.3 standards. The 802.LAN-MAN standards, including Ethernet, use two separate sublayers of the data link layer to operate. The LLC 802.2 places information in the frame to identify which network layer protocol is used in the frame. For example, wireless and copper and maybe Bluetooth. MAC sublayer, it's responsible for data encapsulation and media access control, and it provides data link layer addressing. And I'd like to zoom in on this again just to show you we're talking about these bottom two layers of the OSI model. And we're not talking about IPv6, IPv7 yet. We're still down here at the bottom two layers. Now, the MAC sublayer is responsible for data encapsulation and accessing the media. Data encapsulation includes the following: Ethernet frame. This is the internal structure of the Ethernet frame. I'll show it to you in a couple minutes. Ethernet addressing. The Ethernet frame includes both a source and destination MAC address to deliver the frame from one Ethernet NIC to another Ethernet NIC, the next hop in our LAN, or the next hop to our destination. Ethernet error detection also exists. A frame check sequence, FCS trailer, is used for error detection. Now, the sublayer includes specifications for different Ethernet communication standards over various types of media, including copper and fiber. And that is this green portion here. So we're talking about fast Ethernet, here's fiber, here's just gigabit Ethernet. You get the idea. Legacy Ethernet using bus topology or hubs is a shared half-duplex media. Ethernet over a half-duplex media uses a contentious-based access method, carrier sense multiple access collision detection, CSMA/CD, and we talked about that that contentious-based access method in our previous module 6. If you haven't watched that video, please go back and watch that video. Ethernet LANs of today still use switches that operate in full duplex. Full duplex communication with Ethernet switches do not require that process. So let's talk about the frame fields. So the minimum Ethernet frame is 64 bytes, and the maximum is 1518. If the frame is less than 64 bytes in length, it is considered a collision fragment or runt frame. They're called runts, and it is automatically discarded. Frames with more than 1518 bytes of data are considered jumbo or baby giant frames, and they are also just discarded. And this shows you, it doesn't help to zoom in, does it? So this shows you that 64 to 1518 byte frame and what it should be broken down with the destination MAC address, source MAC, what type of data it is. But notice it can be a minimum of 64 bytes, and it can be, if you add up 45, 47, 53, 59, and 4 more bytes. I wonder where that 4 bytes is. 6, 12, 13, 14. That's 59 plus 4 more. Oh, these 4 bytes, the last 4 bytes. That's the minimum 64 bytes. I was going the wrong way. The first part is not counted in creating the size for the that frame. Now, obviously, if it's less than 64, it doesn't have enough information so there must be a problem with it. And if you add up 15,000 to these other 6, 6, 2, and 4, that's where 1518 comes from. And if there's more than that, we have a problem. You're going to do a lab on this. You're going to use Wireshark to examine Ethernet frames. And I'll let you go learn more about Ethernet with that, the frames. Ethernet MAC addresses. Now, an Ethernet MAC address consists of a 48-bit binary value expressed using 12 hexadecimal values. Given that 8 bits, 1 byte, is a common binary grouping, binary all zeros to all ones can be represented in hexadecimal range of all zeros to FF, which is all ones. We learned about hexadecimal, I believe, in Module 5. If you haven't watched that video, you need to go back and learn about hexadecimal, or watch a YouTube video from somebody else. When using hexadecimal, or you can watch it from me if I've created one of those at some time in the future. When using hexadecimal, leading zeros are always displayed to complete the 8-bit representation. For example, the binary value 0000 1010 is represented by the hexadecimal value of 0A. Now remember, hexadecimal is 0 through 9, and then A, B, C, D, E, F. Those are our 16 values. Now, the reason they tell you that, or take the time to tell you that, is because IPv6 is not that way. When we learn next week, when we're in networking, we'll learn. Actually, I think the week after is when we learn about IPv6. In IPv6, we discard the beginning values, but here if we were to discard these beginning values, we would not know where. If it was just A, we would not know if it's 0A or A0. There would be no way to know that. So you can't get rid of the leading zeros. I guess if it was A, you could. They just don't. Okay, hexadecimal, you show all the zeros. There's not a lot of them, so you're good. IPv6 is 128, so I guess that's why they make a difference. Hexadecimal numbers are often represented by the value preceded by a 0x. For example, 0x73, that means it's hex instead of decimal or binary. Hexadecimal may also be represented by a script 16 or the hex number followed by an H. Subscript 16. In an Ethernet LAN, every network device is connected to the same shared media. MAC address, and that means on each side of a connection, it's the same type of data. MAC addressing provides a method for device identification at the data link layer of the OSI model. An Ethernet MAC address is a 48-bit address expressed using 12 hexadecimal digits. And those 12 hexadecimal digits are broken down into two 6 hexadecimal places. Because a byte equals 8 bits, we can also say that a MAC address has 6 bytes in length. All MAC addresses must be unique to the Ethernet device on the internet, not just on the, I guess, yeah, let's just go with on the internet. They must be unique. Now, to make that happen, all vendors that sell Ethernet devices must register an OUI. An OUI stands for Organizational Unique Identifier, and it is the first 3 bytes of the MAC address. So this portion of our MAC address identifies the OUI. If you were to, well, you're going to do a lab where you're going to do this, but if you were to go into your, on your PC, if you were to do an ipconfig /all, you'll see your MAC address. You take the first 6 bytes, the first 6 hex values, and you Google that, you will find, and with the word MAC, you will find the manufacturer or the vendor of your NIC. The last 6 value placements are unique from 1 to 000, I should say, all zeros to all Fs. And when you see, and that is, would be all of the possible NIC cards that were created. So they're all zeros. So the first OUI, for example, from Dell, they buy a new OUI, and the first address is obviously all zeros, and then 0000, all zeros, and then a 1, and then a 2, and all the way till you get to FFFFFFF. And that is how MAC addresses are created. Now, when a frame processing, so when a frame is forwarded or forwards a message to an Ethernet network, the Ethernet header includes the source MAC address from where the message is originating to the destination MAC address. That's the next hop. Remember the last video in Module 6, I said it's important to remember MAC addresses, NICs, are just from hop to hop to hop to hop as it's going through a network. When a NIC receives an Ethernet frame, it examines the destination MAC address to see if it matches the physical MAC address that is stored in RAM. If there is no match, then the device discards the frame. If there is a match, then it passes the frame up the OSI models where the decapsulation process takes place. That means you've reached your destination. If it's the right MAC address, that's where it belongs. Now, it's going to get to, just to get a little ahead, it's going to get to layer 3 of the OSI model, which is the network layer, which if it isn't the right IP address or IPv6 or IPv4 address, it will say, oh, that's not the right place. Let me look in my routing table to see. This is happening at layer 3, which is next week's presentation. It's going to look in the routing table. It's going to say, hey, am I this IP address? If it's not the IP address, then it sends it back down to the, then it looks in the routing table and says, do I know where to send it? If I know where to send it, then it sends it back to the data link layer saying, hey, this isn't me, but I know where to send it. You need to send it to this other MAC address, right? This other place. And then off it goes. The MAC address, the CAM table. We'll talk about that in a second. So so if it is the location, if it is the right IP address, then it keeps sending it up the OSI model. So again, the MAC address layer 2 will determine if it's the right address for the packet. If it is, then it sends it up to the networking, which determines if it's the right IP address. If it's the right IP address, then it keeps going up the OSI model. If it's not the right IP address, then it determines whether or not it knows where that IP address is. If it does, it sends it back down with that information. If it doesn't know, but it has a default gateway, it sends that down and says that I don't know where it is, but let's send it on to the default gateway. And then it sends it down to the data link layer. And then the data link layer says, okay, let's re-encapsulate it in the correct modality, whether it's wireless, fiber, copper, and let's go ahead and send it back to the physical layer to send it back out as ones and zeros out to the next hop. The MAC address changes, but the IP and destination does not. I hope I haven't given you too much information there just to confuse you. I'm hoping that helps to kind of show you where we are with this, what happens when it receives the frame at that layer 2 level. Note, Ethernet NICs will also accept frames if the destination MAC is a broadcast or a multicast group, which we'll talk about in a minute. So back here, if these are all Fs, that's a special MAC address. And when a device sends out all ones, FFFF, if it sends out all ones, that's a broadcast address. And then there's also a multicast MAC address I'll show you in a little bit. Any device that is the source or destination of an Ethernet frame will have a unique Ethernet NIC with a unique MAC address. I guess the network interface card isn't really unique. You buy a model, but it is unique because it has a physical address attached to it. I'm going to leave that there. It is possible to trick people by changing your MAC address using software, but it's a burned-in MAC address, so it's unique for each NIC. So ultimately, each NIC is unique. This includes workstations, servers, printers, mobile devices, cell phones, tablets, routers. In Ethernet, different MAC addresses are used for layer 2 unicast, broadcast, and multicast communication. A unicast MAC address is the unique address that is used when a frame is sent from a single transmitting device to a single destination device. The process that a source host uses to determine the MAC address with an IPv4 address is known as Address Resolution Protocol, ARP. So when you hear me saying that a switch sends out an ARP request to determine a MAC address, that's what we're talking about. Address Resolution Protocol. It's so that it knows where to send that that unique address to only one, ultimately one device. We'll learn that in a video in a few minutes. The process that a source host used to determine a destination MAC address in an IPv6 system is known as neighbor discovery ND. The source MAC address must always be unique, and that's because it's coming from one device. It's coming from this guy. Here's its MAC address, and it is unique. It's going to this guy, but if it doesn't know the address, it has to use neighbor discovery for IPv6. It has to use ARP to determine where is that address, and we learn that a little bit later. Again, source MAC address, destination MAC address. If it doesn't know the destination MAC where the destination MAC address is, it sends out an ARP in IPv4 and neighbor discovery in IPv6. Notice the source and destination remains the same, the actual data, and then a trailer including to determine if there's any damage, and that is our Ethernet frame that is sent out over the physical layer to search the world. Now, a broadcast frame is received. Nope, I don't want to do that yet. An Ethernet broadcast frame is received and processed by every device on the Ethernet LAN. The features of an Ethernet broadcast are as follows. It has a destination MAC address of FFFFFFF. In hexadecimal, it's 48 ones. It has flooded out all Ethernet switch ports except for the incoming port. It is not forwarded by the router. Now, by the way, this is only true. It is. If it is a broadcast, it is going to everybody, but it is not going back to the original source. So it's broadcast. It's going to everybody, just like a bullhorn broadcast or FM broadcast. It's going to everybody that has an FM radio to be able to pick up that signal. If the encapsulated data is an IPv4 broadcast packet, that means that the packet contains the destination IPv4 address that has all ones in the host portion. This numbering in the address means that all hosts on that local network broadcast will receive and receive and process the packet. Everybody gets it. They could have done it in 3 words. Now, multicast, just like it sounds, goes to some. It goes to some addresses. It goes to these 3, but not those 2. Okay? So remember, we still start with a unicast address because H1 in this case has a unique MAC address on its NIC card. So this is unique. And then, this is unique. And then it has a destination MAC, and this is a special address this is a destination MAC address that's unique, 0000C8. That says I am a broadcast. There was a destination MAC in that example. So in this, there is a destination MAC address of 01005E, for example, when the encapsulated data is an IPv4 multicast packet and a destination MAC address of 3333 when the encapsulated data is an IPv6 multicast packet. There are other reserved multicast destination MAC addresses for when the encapsulated packet is not IP, such as spanning tree protocol. It has flooded out all Ethernet switch ports except for the incoming port, unless the switch is configured for multicast snooping beyond the scope of this class. It is not forwarded by the router. So if there was a router here also connected to the switch, the router would not broadcast it again. Other switches may. Oh, they will. Other switches will, but not a router. Remember, networks are unique in router. Each connection on a router is a unique network. Easy to remember. Because the multicast addressing represents a group of addresses, sometimes called a host group, they only can be used as the destination of a packet. The source will always be a unicast address. As with the unicast and broadcast addresses, the multicast IP address requires a As with unicast and broadcast addresses, the multicast IP address requires a corresponding multicast MAC address. You're going to do a lab where you're going to get to look at MAC addresses and have fun with that. The MAC address table. Now, a layer 2 Ethernet switch uses a layer 2 MAC address to make forwarding decision. It is completely unaware of the actual data being carried in the data portion of the frame, such as an IPv4 packet or an ART message or an IPv6 neighbor discovery packet. It doesn't care what it's carrying. It just cares about the next MAC address. The switch makes the forwarding decision based solely on the layer 2 Ethernet MAC addresses. An Ethernet switch determines its MAC address table, examines its MAC address table to make a forwarding decision for each frame. Unlike legacy Ethernet hubs that just repeated the bits out of all ports except for the incoming port. When a switch is turned on, the MAC address table is empty. So I'll come back to that in a minute. The MAC address table is sometimes referred to as the contract addressable memory table, the CAM table. So a MAC address table is also a CAM table. Don't be confused when they interchange the terms inside of this module and in life. So how does the switch learn and forward? Well, it needs to examine the source MAC address upon ingress. Every frame that enters a switch is checked for new information to learn. It does this by examining the source MAC address of the frame and the port number where the frame entered the switch. If the source MAC address does not exist in the CAM table, it is added to the table along with the incoming port number. If the source MAC address does exist, the switch updates the refresh timer for that entry. Although it is variable, by default, most Ethernet switches keep an entry in the CAM/MAC table for 5 minutes. If the source MAC address does not exist in the table, but if it does exist in a table but on a different port, the switch treats it as a new entry. The entry replaces the same MAC address but on the new current port. Now, the reason you might have this is we're going to learn later in Cisco 2 that you might have multiple connections between devices as redundant connections or as a way to increase the speed between the two devices. If that is true, then you'll really learn this more later, but there are two devices connected to each other on both sides. They have the same MAC address on both sides is the same. So ultimately, you might get a loop there. You might get, hey, I come in here, oh, but I'm going out there, and around it would go. We talk more about that later in another module in Cisco 2. So I'm not going to get too far into it here. You can jump ahead and go watch that video if I've released it already and learn about it. It also would happen. Let's say you're trying to get the PC to work and the PC next to you works, but your connection to the internet doesn't work. Their connection works. Maybe you disconnect the cable from your computer and plug that Ethernet cable into the other computer, and then if there's no security enabled, which there should be in every network system, then the switch is going to see that traffic coming from the same PC but on a different port. It would just switch it over. If the destination MAC address is a unicast address, the switch will look for a match between the destination MAC address of a frame and the entry in its MAC address table. If the destination MAC address is in the table, it will forward the frame out that specific port. If the destination MAC address is not in the table, the switch will forward the frame out all ports. Remember, it's called ARP. It will send it out all ports. This is called an unknown unicast. If the destination MAC address is a broadcast or a multicast, the frame is also flooded out all ports except for the incoming port. Filtering frames. Now, I have videos to show you this, so I'm not going to get too deep into this because you're going to see it in a minute. But as a switch receives the frame from different devices, it is able to populate its MAC/CAM address table by examining the source MAC address of every frame it receives. When the MAC address table of a switch contains the destination MAC address, it is able to filter the frame and forward it out a single port. It does not need to send it out everywhere. It sends it out just one port. In this case, the frame is coming in on from MAC 000A, and the destination is 000D over here. So it comes in port 1, and it is not flooded because it knows where to send it. It sends it to B directly. Switching in networking. Two terms are associated, and I've used one of them already, ingress. That's that's when the frame is entering the interface. Egress is when it's exiting the interface. Remember, learning happens, a switch learns the MAC address and adds it to the MAC table on ingress. It uses that MAC address to make forwarding decisions. A switch will never allow traffic to be forwarded out the interface where it received the traffic. Oh, and all they're showing you here is that each port, all 6 of them, are all known on the MAC table, on the MAC address table, the CAM table. They're all known. So port 1 is EE and port 2 is AA. Now, just to clarify, if you're confused by why all these letters keep changing, the NetAcad has taught you that a MAC table has 12 hexadecimal values. Now, for some random reason, they just change how they present it. Here, EE is representing all 12 values of the MAC, and all 12 values would be stored. Earlier, where it showed OA, again, this is representing all 12 values of your MAC address. Don't be confused by that. A switch will use the destination MAC address to determine the ingress. Destination will use the destination MAC address to determine the ingress interface. No, the egress. Okay. What they're saying there in really poor wording is they're saying they're going to look at the MAC address to figure out where it's going to send it. Before a switch can make this decision, it must learn what interface the destination is located on. A switch builds the MAC address table, also known as the CAM address table, by recording the source MAC address into the table along with the port as it is received. This video will explain how the switch builds its MAC address table by recording the MAC address of each device connected to a port. And this shows how it will build its MAC address table, and here we go.
In this video, Pete PCA is going to send an Ethernet frame to PCB, and PCB is going to send an Ethernet frame to PCA. We're going to examine how switches S1 and S2 build their MAC address tables, and also how they forward frames based on the information in those MAC address tables. PCA has an Ethernet frame to send to PCB. The source MAC address of the frame is 000A, and the destination MAC address is 000B. The Ethernet frame is sent to switch S1. S1 receives the Ethernet frame, examines the source MAC address, and notices that this MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number. Next, switch S1 examines the destination MAC address and notices that this MAC address is not in its table, so it floods it out all ports. PCB receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices that that is a match and receives the rest of the frame. The Ethernet frame continues to be forwarded to switch S2. Switch S2 examines the source MAC address of the frame and notices it is not in its MAC address table, so it adds the MAC address and the incoming port to its MAC address table. Next, switch S2 examines the destination MAC address, notices that is not in its MAC address table, so it floods it out all ports. PCC receives the Ethernet frame, and its MAC address does not match the destination MAC address of the Ethernet frame, so it does not accept the rest of the frame. The router receives the Ethernet frame, examines the destination MAC address against its own MAC address, and knows it is not a match, so it does not receive the rest of the frame. Now let's have PCB sending a frame back to PCA. The source MAC address of the frame is 000B, and the destination MAC address is 000A. PCB sends it to switch S1. S1 notices that the source MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number. Next, switch S1 examines the destination MAC address and notices that MAC address is in its MAC address table, so it sends it out just port 1. PCA receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices it is a match, so it receives the rest of the frame.
Okay, hopefully that makes sense. And then there's another video. What if the destination is not in the local network? What if it is in outside out on the internet? Well, it has to go to the default gateway. And this is a video to show you that concept.
In this video, PCA is going to send a packet to the internet because the destination IP address is on another network. So in this case, the source MAC address is that of PCA. The destination MAC address is that of the router of 000D. So the Ethernet frame is sent to switch S1. Switch S1 receives the frame, examines the source MAC address, which is in its MAC address table. So it just simply refreshes the 5-minute timer. It examines the destination MAC address, and because that destination MAC address is not in the MAC address table of switch S1, it floods it out all ports. PCB receives the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the frame. Switch S2 receives the Ethernet frame, examines the source MAC address, which is in its MAC address table, so it also simply refreshes the 5-minute timer. It examines the destination MAC address of the frame, which is not in its MAC address table, so it floods it out all ports. PCC gets the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the Ethernet frame. The router receives the Ethernet frame, and because the destination MAC address does match its own MAC address, it accepts the rest of the frame. Now we'll look at the Ethernet frame coming from the router back to PCA. The source IP address is the IP address actually of a device on a remote network. The source MAC address is that of the router at 000D, and the destination MAC address is that of PCA. The frame is sent to switch S2. S2 receives it, examines the source MAC address, which is not in its MAC address table, so it adds it. It then examines the destination MAC address, which is in its MAC address table, so it forwards it out port 1. S1 receives the Ethernet frame, examines the source MAC address, which is not in its MAC address table, so it adds it to its MAC address table. It examines the destination MAC address, which is in its MAC address table, so it goes ahead and just forwards it out port 1 towards PCA. PCA examines the destination MAC address, and because it is a match, it accepts the rest of the frame.
All right. Hopefully that was a useful video for you. Let me see. Is there another one? Nope. You're going to do a lab. Before I leave this, let me make sure. Yeah, we just did the default gateway. All right. So there was a question asked, why is it only a 5-minute frame timer? Well, something you may not be aware of is that the routers in general do not know about the entire internet. That's for the higher level domains to pay attention to the entire internet. All your router really knows about is what is communicated via RIP or EIGRP or OSPF. That's all it knows about, and that's all it maintains in its own routing table. Now, a switch is the same thing. A switch only knows about what's connected to it, and devices that are connected to the switch are talking to it all the time. So the device, 5 minutes, if you haven't talked in 5 minutes, there's a good chance you've been disconnected. So it is removed from the CAM table if it's longer than 5 minutes. The same thing's true with IP addresses and routing information for routers. It's not kept in the routing table forever. Just because you know how to send a packet one time to get to a destination does not mean your router is going to use that same information the next time. You actually don't want it to, because that's the beauty of the internet. It will always find the best path to a destination unless you have statically configured a path inside of your router. It will always find the best path, and then the next time around it could be a different best path. So the same thing can be in this case when it comes to switches. Switches don't need to keep all that information because when it needs it, it can do it fast enough using either neighbor discovery or ARP, and then it's good for 5 minutes and your device gets reconnected. Hopefully that helps answer the question that was posed. All right, now we'll talk about switch speeds and forwarding methods. Switches use one of the following forwarding methods for switching data between network ports. You can use store and forward, or you can use cut through. And then cut through has 2 methods. So there's really 3 methods, but there's 2 methods up front. Store and forward switching, this frame forwarding method receives the entire frame and computes the CRC. The CRC is your to determine that the frame is valid. If the CRC is valid, the switch looks up the destination address, which determines the outgoing interface. Then the frame is forwarded out the correct port. Cut-through switching, on the other hand, this frame forwarding method forwards the frame before it is entirely received. At a minimum, the destination address of the frame must be read before the frame can be forwarded. A big advantage of store and forward switching, the one where the whole part is read, is that it determines if a frame has any errors before it propagates the frame through the network. When an error is detected in the frame, the switch just discards the frame. Discarded frames with errors reduces the amount of bandwidth consumed by corrupt data being transferred through the network. Store and forward switching is required for quality of service QoS analysis, like IPv phones and video, or converged networks where the frame classification for traffic prioritization is necessary. For example, voice over IP data streams need to have priority over web browsing traffic. In cut-through switching, the switch acts upon the data as soon as it is received, even if the transmission is not complete. The switch buffers just enough of the frame to read the destination MAC address so that it can determine to which port it should forward out the data. The switch does not perform any error checking on the frame. Now, as I mentioned a moment ago, there are two methods of cut-through switching. There's fast-forward switching, and there's fragment-free switching. Now, fast-forward switching offers the lowest level of latency by immediately forwarding a packet after reading the destination address. Because fast-forward switching starts forwarding before the entire packet has been received, there may be times when packets are relayed with errors. The destination NIC discards the faulty packets upon receipt. Fast-forward switching is the typical cut-through method of switching. Now, fragment-free switching is a compromise between high latency and high integrity of store and forward and the low latency and reduced integrity of fast-forward switching. The switch stores and performs an error check on the first 64 bytes of the frame before forwarding. Because most network errors and collisions occur during the first 64 bytes, this ensures that the collision has not occurred before forwarding the frame. Now, switches have memory buffers. They can have two different types of memory buffers. They can have port-based buffers, and they can have shared memory. Now, port-based memory, frames are stored in queues that are linked to specific incoming and outgoing ports. A frame is transmitted to the outgoing port only when all frames ahead of it in the queue have been successfully transmitted. It is possible for a single frame to delay the transmission of all of the frames in memory because it's waiting on that one frame to be processed. This delay occurs even if the other frames could have been transmitted to open destination ports. I like to think of this as Disney, right? Or at a bank or a drive-through, since we don't go into banks much anymore, a drive-through at a bank, you're in a line, you pick that line, you're stuck in that line, no matter if the person in front of you is doing one short transaction or taking care of their entire company's business, you are stuck in that line. Shared memory, on the other hand, deposits all frames into a common memory buffer shared by all switch ports, and the amount of buffering memory required by a port is dynamically allocated. In shared memory, the frames in the buffer are dynamically linked to the destination port, enabling a packet to be received on one port and then transmitted on another port without moving it to a different queue. Now that is like let's say you're at the grocery store and they have one long line that opens up to 4 or 5 self-service registers, right? One line, 4 or 6 self-service registers. Whichever one's open gets the next frame and off it goes. So it needs to, it can be, the memory is shared. I don't know if that's a perfect way, but just the memory is shared, and you can ultimately have less memory because in the machine, because instead of having a lot of memory for ports that you're not even using in the switch, for example, maybe you only have 8 out of 24 ports connected, you'd have port-based memory, you'd have to have a set amount of memory for each port, even the 16 that are not used. Whereas shared memory, you would have one big pot of memory that the 8 would be able to use, and if there's only 8 being used. Shared memory buffers also result in larger frames that can be transmitted with fewer dropped frames. This is important with asymmetrical switching, which allows for different data rates on different ports. Therefore, more bandwidth can be dedicated to certain ports, for example, a server port. Duplex and speed settings. Two of the most basic settings on a switch are the bandwidth, speed, and duplex settings, which we've already talked about, for each individual switch port. It is critical that the duplex and bandwidth settings match between switch ports and on each side and the connected devices. There are 2 types of duplex settings used for communication, and we've talked about them. Full duplex, where both ends can communicate at the same time, and half duplex, where only one can communicate at a time, walkie-talkie. Auto negotiation is the optional function found on most Ethernet switches and NICs. It enables 2 devices to automatically negotiate the best speed and duplex capability. And that can create problems. It also can help configure the network. Once you connect it, it can determine your full duplex and just keep going. Gigabit Ethernet ports only operate in full duplex. Duplex mismatch is one of the most common causes of performance issues on 10/100 megabyte Ethernet links. It occurs when one port on the link operates in half duplex while the other operates at full duplex. This can occur when one or both ports on a link are reset, and the auto negotiation process does not result in the same configuration. It can also occur when users reconfigure one side of the link and then forget to configure the other side. Both sides of the link should have auto negotiation on, or in a better situation, both sides should have it off. Best practice is to configure both Ethernet port settings as full duplex without auto negotiation. Just configure both sides as full duplex in a full duplex system. Then you don't have to worry about the configuring what happens if you turn off a piece of equipment and then it reconfigures incorrectly when you turn it back on again. Auto-MDIX. Connections between devices require the use of either a crossover or a straight-through cable. The type of cable required depends on the type of interconnecting devices. For example, or examples, a direct connection between a router and a host requires a crossover cable. Think about it. A PC is the same, a router is the same thing as a PC. It's just a specialized computer. They're the same. So they talk on the same lines and they listen on the same lines, right? So a router and a host, router and a PC, or a router and a server have to be on a crossover connection so that and I always kind of mess this up, so that the talking sides are on different lines. I hope that helps. Connections between different devices, for example, a router and a switch, require a straight-through cable because they're communicating on different lines. Most switch devices now support the automatic medium-dependent interface crossover, better known as Auto-MDIX. You may not see that again in this course, automatic medium-dependent interface crossover. If you ask me what Auto-MDIX stands for tomorrow, I won't be able to remember that. And I've been teaching this course for a very long time because we call it Auto-MDIX. When enabled, the switch automatically detects the type of cable attached to the port and configures the interface accordingly. Now, the Auto-MDIX feature is enabled by default on switches running iOS release 12.2/18 or later. However, the feature could be disabled. For this reason, you should always use the correct cable type and not rely on Auto-MDIX. For example, in a test configuration in a classroom, your devious professor could turn that off, and if you just grab any cable, it could create a problem. Now, for you, it won't work. Now, to solve that problem, you can re-enable MDIX with the MDIX auto interface configuration command that is made on the interface itself. That's where you run that, not in global, because each interface on a router can have different configurations. So remember, you have to go to the interface and enable MDIX by using MDIX space auto. Any questions? That is the end of the presentation. I'm going to stop sharing. Now, we're going to have a moment in just 2 or 3 minutes to ask questions if you're here with me live. If you are watching this presentation online, I want you to go ahead and ask your questions in the help discussion forums. We'll all help you answer those questions. And if you are watching this on YouTube, please like and subscribe down below and ask your questions. We'll help you. I'll help you. We'll all help you understand the concepts. My name is Don Lafond, Professor Don. It's my pleasure to help you learn Cisco. That's the end of this presentation today. I hope you are here to see the next module, which we will talk about the networking layer of the OSI model. And that's when things get fun with talking about IPv4 and IPv6 in the following module. So enjoy this module. It gets a little bit more fun when we get to the next module. Thanks for coming to class. I'll see you again soon.